Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 1029, two-city scheduling. In the problem description, we're told that we're given a company which is planning, or that is planning to interview 2n people, given the array costs, where costs I is equal to the cost of sending a person to city A or city B. We want to return the minimum cost to fly every person to a city such that exactly n people arrive in each city. So in simple terms, we want to send half the people to city A, and we want to send half the people to city B. Okay. And in this example is kind of misleading because if you think about it, we're only choosing the minimum values here. So city A and city B. So you might say, why don't we just always choose the minimum values and boom, this is now an easy problem. But that's not the case. Let's say this was 200. Well, then this and this person would end up at city A, and then we only have one person at city B, and that's not allowed because that would be odd, and we need it to be even. We need half the people to be at A and half the people to be at B. So how can we quantify whether or not we want to send a person to A or B? Well, let's create a more simple example. I don't know, something like 2,200, let's say, and then 22,000. Okay, so what I can do is say, to us at a glance, this makes the most sense is to send this person city B, city B, and send this person to city A, because the total will be what, 220. Whereas if we sent this person to city A and this person to city B, well, then we would get a total of 2020, and that's way bigger than 220. So we want to choose the smaller cost, because we want the minimum cost to fly every person, not the maximum. So let's quantify this, right? How can we know which is cheaper? Well, we can simply just do the subtraction, right? How much more expensive would it be to send this person here, to city B as opposed to city A? How much more expensive would it be? Well, 200 minus 20 gives us 180. So it would cost us 180. I'm assuming whatever the currency is, dollars, to send this person to city B as opposed to city A. But wait a minute, we don't want to just stop here. Doesn't mean we send this person to city A still, because it could be that, let's check the next element. Well, how much more expensive would it be to send a person to city B as opposed to city A? Well, it would be $1,980 more. So it's a lot cheaper to send this person to city B as opposed to this person to city B. So that's how we can quantify it. We can basically just calculate the difference. And then we want to sort our list based on the difference. So we want to have the smallest, so we'll have, 180 here, and then we'll have 1980 here, and we will put everything in the first half. There's only two elements here, but obviously it could be, multiple. So we'd put everything in the first half would go to city B because it would be cheaper to go to city B, and then the rest would go to city A because it would be cheaper to go to city A. So I hope that that intuition makes sense. Let's actually get to coding this problem. So the first thing we want to do, of course, is sort according to the key that we wanted, and this is going to be a lambda function, an inline lambda function, x, where x1 minus x0. So we want all of this, the costs that would be cheaper for city B first as opposed to city A. So then we want to calculate n, which is going to be half of basically the length of the costs divided by 2. So the length of the costs divided by 2. And then we want to have a result variable. So we'll have a result variable, and then all we have to do is say for I in range of n, all the numbers up to the first half, result plus equals costs of I 1, because we want to send all of these, the first half, all of them, we want to send to city B. The second half, we want to send to city A, and we want to say everything from n to 2 times n. We will add u to city A because it will be cheaper to send u to city A as opposed to city B. And then we just want to return the result. So let's submit our code and let's check that works. And it does. We pass all 50 test cases for this problem with a very optimal solution that beats 100% of all problems. So yeah, there are ways to do it. I think, you can kind of go like a binary tree solution. There is, I do believe there's like a DP problem as well, DP solution, but this is the most optimal solution in terms of how easy it is to derive. And also obviously, as you saw, the time and space is also, also the time complexity is also pretty optimal. So easy to come up with, and also easy to code up. But a bit hard to spot that this is a greedy problem. Once you understand the greedy element of it, it's a lot easier to code up. So in terms of time complexity, well, it's going to be, we are sorting, so it's going to be big O of n log n, big O of n log n. Space complexity is just big O of 1 because we're not using any extra space. So with that being said, I hope you guys enjoyed this video, and I'll catch you in the next one.